Good morning. Thank you for being here. I hope you're as excited as I am. My name is Andy LoPresto. I'll be presenting about Apache MiNiFi and how we can use that platform to do secure command and control and data exfil and ingest from industrial IoT. So a brief overview of the presentation today. I'll introduce the topic and a brief introduction of data flow concepts just to make sure that we're all on the same page. I'll go into the tools Apache NiFi and Apache MiNiFi, and unfortunately not do a live demo because the desk is kind of small and airport security doesn't like when I bring my big case full of exposed wires and circuits and things through. But I do have some videos and images of some stuff, and then we'll take questions at the end. For anybody who doesn't want to ask questions in person or is like me and forgets them by the end of the presentation, you can go on to Slido and enter it that way. So this presentation is for an audience that is new to data flow concepts and to the Apache NiFi and MiNiFi platforms. So I will give a brief introduction and cover the foundations for everybody to be on the same page. On the right there, that's Yolanda Davis, who's one of our smartest engineers, and she could do these talks with her eyes closed. So who am I? I am a committer and PMC member for Apache NiFi. I'm also the manager of the Data in Motion Engineering Security team at Cloudera, and we focus on keeping both our customers and our users safe, and their data safe as well. I travel around presenting at a lot of conferences like this, engaging with customers, getting a lot of great feedback and hearing how people are using the platform and what problems they have in their daily lives that we're not yet solving. So I really encourage feedback and I look for that communication and conversation to help us build a better tool. And I'm also introducing some of the IoT hardware and monitoring systems in a brewery in El Segundo, California. So the simplest question that we're going to address today, what is data flow? Well, data flow, very simply stated, is moving some content from point A to point B. And the content could be anything. It could be arbitrary bytes. It could be text in logs or JSON or CSV format. It could be binary like images, video, and telemetry, things like that. The two terms I really want to take away here is we start with producers, so anything that creates data, and we send that data over to consumers. And that could be other hardware systems, that could be long-term persistence, or that could be humans who are consuming that information. So moving data is fairly easy, and I think we've all done that in our lives at some point. But moving data effectively can be very difficult. As usual, XKCD illustrates this quite nicely with the concept of these bespoke data movement systems, which are quite often house of cards, right? They fall apart very easily. As soon as you get one piece of data that doesn't fit your preconceived notion of what it should look like, the whole system falls apart. So this slide will be up here for about 18 minutes. No, I'm just going to talk very briefly about one from each column, but we have problems around the data, problems around infrastructure, and problems around people. Okay, so even if we solve everything from the first two columns, we solve every technical issue that we could ever encounter, we still have issues around how we interact with people. And one of the ways that we encounter this is that consumers can change. Okay, so anybody who's worked for a company where you have engineers and you have data scientists, and the data scientists all sit together, and that's great. We get the value of all of their contributions and collaboration. And then a new CTO comes in and says, well, this is very siloed. All the data scientists are by themselves, and they're not really engaging with the rest of the organization. So I want to embed a data scientist on each engineering team so that we move that much closer to the source of the data. We are going to get all this new information and learnings, and it's going to be great. Do you have a system where you can very quickly change where all of your data is going from one centralized data source and data collection system into sending it out to 15 different teams, right? So then you have to have IT build a whole new system to do that, and that takes about 6 months. And 7 months, you get a new CTO, and they say, why are we wasting this? Why do we have one data scientist here and one data scientist here and one over there? We should make a data science team where we can get all of this expertise in one place. So let's move all those data scientists together into one place. Now, can you just flip one switch and have all the data that was going out to those different teams go to one location? And what happens to the data that was going to each of those teams over the last 6 months? Can you recover all of that data and move it back into one place so they can get these insights? Hopefully the answer to this is Apache NiFi. So again, a very brief introduction to the ecosystem. Apache MiNiFi is a very robust piece of software. It runs on server-class hardware in data centers. It is designed to manage the entire lifecycle of data flow, so it provides a nice web user interface, as well as a fully functional REST API. Anything that you can do with the user interface, you can do with the API. In fact, it is a reference implementation. It interacts with hundreds of services, and I'll discuss a little bit more later, but basically anything that's been on the Apache homepage for the last few years, MiNiFi can interact with out of the box. So if you're like me, you're very comfortable in the terminal, and I spend most of my time there. But if you're not a developer, you're not a coder, but you still work in an environment where you have a lot of expertise about the data that you're getting or the systems you're getting it from, how do you build the systems to ingest that data? Well, with MiNiFi, we move from an interface like this to more of this, right? Giving you that graphical interaction where it's very easy to drag and drop processors onto this canvas, connect them with arrows, and then see the data flowing in real time. We want to remove the barriers of entry and allow non-technical users to also contribute because they often have some of the best expertise around what the data means, right? For a lot of data scientists, data engineers, people like myself, we can look at bytes and see that as, okay, this is formatted in this way, this meets a certain protocol specification, things like that, but the value of the data isn't necessarily apparent. If you don't have the domain expertise, if you haven't worked in that industry or in that field, you might not know what this means. I saw a data scientist once spend a week trying to figure out what was wrong with their model, tweaking, because the number kept coming out negative. And somebody who worked as a bank teller was like, yeah, well, because that's a rate, and that's a negative rate. That makes sense. But the data scientist had no idea because in their mind, the model should have been coming out with a positive number. They just didn't understand what the context was around the information. Now, it's not only a no-code solution. You can certainly extend it via custom scripting, via custom processors, via invocation of the API. But if you're looking for something where you don't have to write code in order to provide these data flow platforms, then this is a good solution for that. This slide is mostly in so that when you go back and look at the slides later, you can see all these nice features, but I'm not going to waste a lot of time here. As I did mention earlier, there is out-of-the-box integration with a huge number of services. So especially in the big data realm, things like Kafka, Avro, Spark, Flink, these are very often other services that we need to interact with, either because that's where our data is coming from or that's where it's going to be consumed. And MiNiFi works very much like the glue in this system. We're not here to provide complex event processing or stream joining or analytics. We're here to make sure that the data gets from where it's coming in the format that it's coming in, to where it needs to be in the format that it needs to be, and do that in a repeatable, robust manner. So I don't know how familiar everybody is with the show Portlandia out of the United States, but in this example, these are two people at a restaurant, and they want to order the chicken, but they're very concerned with where the chicken grew up, how much space the chicken had to run around, what the chicken was fed, how many friends he had. And so they're asking all these questions to the waiter. And it goes on for minutes. And finally, the waitress comes back with a full dossier on the particular chicken that they're going to eat. People want this data around the information that they're consuming, just like they do around the food they're consuming. With Apache MiNiFi, we have a concept called data provenance. And this is metadata that tracks everything that has occurred to the data flowing through your system, from the point of origin, or the point of initial consumption, all the way through transformation, routing, encryption, filtering, persistence, so that not only can you go back and audit this information over long periods of time, you can use this to avoid data poisoning. So for example, in a modern office building where you have temperature sensors throughout the building, 30 degrees centigrade is a fairly high number to read on an internal temperature, right? If this room was 30 degrees, we'd be a little uncomfortable right now. 40 degrees, quite unusual. That really indicates something's happening. But 400 degrees, right? Either your sensor is broken or the building's on fire, right? These are not good scenarios to have. If you're aggregating all of this information and now you're looking at statistics that you've calculated from all of this, if you have a few various sensors that have been broken and they're feeding poison data into your system, do you have the capability to go back and trace that and exclude that information? Or have you now poisoned the entire collection of data that you had up until that point? Not only does it allow that, it allows you to replay data. So let's say it's 3 a.m. on Friday and somebody's hardware fails and they're no longer collecting the data that they should be, but they've been acknowledging that they have been because the hardware failure was transparent to them as well. They didn't have any good monitoring. Monday morning, there's going to be a meeting where somebody's going to be in trouble, right? With data provenance, not only can you demonstrate we did transmit the data, you did acknowledge receiving it, you didn't store it, that's not our fault. But then you can step back and say, look, we're all on the same team. We can replay that data to you. We know which pieces you're missing, and we can send that back again through the exact same flow with very simple couple clicks. So a few examples around what the data flow looks like is some of these example scenarios. Specifically, in this case, I'm going to use healthcare just because I think it's fairly universal to understand. We'll talk about different data, legacy sources, enrichment needs, and data protection. So first is format conversion. I don't know what the makeup of the audience is. I'm assuming some data scientists, some data engineers, some software developers. But raise your hand if you got into this career because you wanted to write a JSON to CSV parser 25 times in your life, right? That's not really interesting problem to solve. That's not new problem to solve. So as an example, by configuring two fields here in a processor, you can ingest XML data and output that in CSV format, right? And this will be automatically updated. It can infer the schema as it's coming in. So if the XML source changes and the ordering changes or some of the specification changes, this can update in real time by using a model to infer what fields are coming in. Same thing with pulling from external sources, right? You very frequently have to ingest data from lots of different sources, and traditionally you'd have to write some kind of connector for each of those things. And that would have to deal with timeouts, with authentication and authorization, with versioning, network connectivity, all these issues. Again, by configuring these existing processors with the kind of connection data that you're already going to be getting, this example is from Azure DB. So on the page with Microsoft where you set up the database, you get these values, you populate them right into the processor, and now you're up and running, pulling data from a SQL database located somewhere else in the cloud. Enriching data. So imagine that in a hospital setting, each bed has blood pressure monitor, heart rate monitor, all of this special machinery by each bed. Now, those machines are often quite old, and the purpose is not to store a full account of each patient that passes through the hospital. The purpose is to read a certain biometric measurement and transmit that. Usually, that information that comes out of a time series has two values. One is the timestamp, and one is whatever particular value, if it's heart rate or blood pressure. There's nothing in there that indicates the patient's age, the patient's medical history, things like that. You get some unique identifier from this is machine 27. Well, pulling that data stream and then in real time enriching it with, oh, I know that machine 27 is in this room. I know the patient who's in this room at this time. I have the patient health history in my completely different database. I can pull from that and enrich that stream of data as it's flowing. So now I have a lot more context over what's actually happening with that individual person, as well as with all the patients in the hospital. I can start looking at patterns across all those people in real time. Finally, data protection. I am a security engineer, so I have to slip this in every once in a while. Out of the box comes with support for, I think, 27, a number of ciphers and encryption algorithms, both symmetric and asymmetric. So especially in the IoT realm, when you're deploying these devices that may not be in your physical control, you can use asymmetric encryption to avoid exposing any sensitive keys. So let's talk about Apache MiNiFi. First of all, the challenges around IoT. I think some people are in the room maybe just because IoT was in the slide title, right? And it's a very, very different and interesting world than a lot of the traditional data collection that we've done. So, IoT challenges, though, often a restricted platform or software library, certainly power and cost consumption restraints, as well as a lot of competing standards and protocols because this is a fairly new realm, right? We're seeing a lot of people generate new ideas here, but that often means there's a lack of consistency across the field. The screenshot here is somebody with a front door security camera and a Roomba vacuum robot, both to improve the quality of their life. The Roomba took out the power cable to the security camera, so both of them broke at the same time. So back to our MiNiFi ecosystem, we're talking now about MiNiFi. So this is a much smaller piece of software. This is designed to run as a good neighbor on platforms that were not built to host this kind of data collection software. So we often describe these as agents. They're small pieces of software. There's both a Java and C++ flavor, and they can run on these platforms and extend the reach and key features of MiNiFi out to the edge. And when we say edge, we mean anything that's not basically a data center server. So again, to reiterate, MiNiFi lives in the data center, right? It's on these robust pieces of hardware. It's running in clusters. It's doing a lot of processing and monitoring. But MiNiFi goes out to the edge. We can install it on anything from a laptop, a cell phone, a Raspberry Pi, a custom chipset that's in a connected vehicle, or put it onto legacy hardware, right? So if you have an older server that really doesn't have the bandwidth and processing power to run a more demanding piece of software, you can use MiNiFi in that instance to run with a very small footprint. Now, why build MiNiFi, right? Why not just take MiNiFi and start removing pieces and get it down to a size that's manageable? Well, MiNiFi is quite large. It's over a gigabyte compressed. When you expand that and add in custom features you might want as well, it can grow even larger. And it is designed to run on that robust hardware, so it makes use of the resources available to it. It also provides features that you often don't need in an edge environment. Right? It's unlikely that you're going to be connecting to your Raspberry Pi and trying to pull up a full Jetty instance web user interface in order to make one configuration change. It's unlikely that you're going to be exposing a full-time REST API from an IoT gateway that is just collecting data from a few hardware sensors in your factory. MiNiFi, on the other hand, is built for that. So I'm not going to embarrass anybody by asking them if they remember floppy disks, but I will say I do. And I recently saw somebody say that's just a 3D printed save icon. They didn't know the history of the floppy disk. A couple of versions ago, MiNiFi C++ fit on a floppy disk. And when I say a couple of versions ago, I don't mean 30 years ago, I mean a few months ago. That fit on a floppy disk. So we are very cognizant of the space constraints around the use cases where this would actually be beneficial. And we design it to be as minimal as possible while still providing value. I mentioned that there's both a Java and C++ version of MiNiFi, and those are not they don't have feature parity. The reason is that the Java version exists because it was built to rapidly go to market and bring a lot of the features of MiNiFi into that smaller footprint area. Meanwhile, the C++ version was written from scratch, so as it gains feature parity with the Java version, you see a lot of the interesting mechanics that it can perform in a smaller, more lightweight footprint. To graphically illustrate that, the origin of the MiNiFi Java was literally taking a lot of the MiNiFi code and pulling out features that weren't necessary. So removing the user interface, reducing the size of the framework itself, a lot of the stuff with interacting with HDFS or Hadoop, not really necessary on a Raspberry Pi. And then also reducing the number of components and extensions, so taking out things like, well, actually, it's capable of running any processor that's written for MiNiFi. However, we just don't bundle most of them by default. Now, on the other hand, the C++ version is what a lot of people are interested in because it is smaller, it's more lightweight, it can run without the presence of the JVM. Out of the box, it comes with only 14 default processors. And so when you look at original MiNiFi with almost 300, this seems like a very small number. However, using JNI, you can also run any existing Java processor, and you can write custom Python processors because that's what the kids like today is Python. So we enable Python, custom Python code to be run, and that allows you to really expand, especially to work with a lot of the SDKs that are available for things like a Raspberry Pi or custom USB hardware that runs on that kind of platform. So how does MiNiFi interact with MiNiFi? Well, there's a couple things to take away from this diagram. The first is that, again, when we talk about MiNiFi, we're generally talking about the edge. So connected vehicles, legacy hardware, IoT, spaces where you don't have a lot of memory and processing power to run. With MiNiFi, we're talking about the core. We're talking about these data centers and robust platforms. But if you look at the bottom in this blue and orange, as it shows here, it's not a hard line delineating when to use each. There is a balance point. And so, for example, if you're a large electronics retailer with stores all over the world, and you have credit card processors that connect to the mobile devices. So as you walk around the store, you can check people out, you can help them. They don't have to go stand in line at a cash register. Well, every request that that device sends, you don't want that going all the way back to one central processing system in a data center somewhere in California, right? So you could put what's technically a regional data center in the store in the form of a laptop or a small server, right? And have each mobile device communicate with that directly. So you have much lower latency, much better response, and then aggregate data there and transmit that back to some central data center. So that's why you might bring MiNiFi out closer to the edge and not have to go all the way back to your central system. In the converse, there are times where even in a large data center on these very heavy and expensive machines, you might not want to install MiNiFi. So let's say you had a large Hadoop cluster, right? You're running MapReduce, you have 200 nodes. You want to do instrumentation and log gathering on each of those nodes. Well, it'd be a complete waste of space and processing power to install a full MiNiFi instance on each one of those. But you could put a small couple megabyte C++ agent running on each of those, collect just the instrumentation and log data that you need, and transmit that back to MiNiFi where you have running on a separate cluster and do all of your analysis and routing there. Now, we've talked about putting MiNiFi on the edge and bringing it out to all these different devices, but why? What does it actually provide for us? Well, the first thing where this can be really useful is data tagging and provenance. When you're using a MiNiFi system, that concept of data provenance begins as soon as the data is brought into MiNiFi. So often that is consuming from a Kafka topic, pulling from a database, reading from an HTTP endpoint, reading from MQTT, things like that. But it's very possible that a lot of transformation has happened to the data before it ever got to that point. So we're limiting our visibility into what's happening with the data at the origin, which is especially where it's really interesting to us. With MiNiFi, we can extend that reach out a lot closer to the edge, so maybe all the way to the IoT gateway, maybe even to the sensor that's actually collecting that data, so that we have much better visibility all the way up to the point of that data creation, and we have much better auditing from a security standpoint, from a governance standpoint, to see what's happening with that data, and we can prove what was happening with that data. This is also really useful for governance from the edge when you're talking about geopolitical restrictions. So if anybody does any work in China, GPS data is regulated extremely strictly. It cannot leave the boundary of China. So what does that mean? Well, if you're building a connected vehicle in China and you say, great, we'll collect all this data and we'll send it to AWS and we'll do our processing in the cloud. Can you prove that the AWS instance that you sent that data to is physically located in China? Or did it bounce around the internet first and then maybe end up in China? And how willing are you to take a risk with that? With something like MiNiFi running at the edge, you can make those filtering decisions, those redaction decisions at the edge without any network connectivity at all, and then bundle the data, batch the data, route it to specific endpoints. That allows you to make all of those decisions much faster. And that actually leads into the last point here with low latency decision making. There are examples, again, connected vehicle, where I might be sampling brake temperature, engine temperature, steering wheel orientation, and radio station, all off the CAN bus. And I'm doing that hundreds or even thousands of times per second. I'm transmitting this data back to a central collection system. I have two wireless radios, actually in this example, on this chipset, two wireless radios, one using LTE and one using Wi-Fi. And when I'm in a downtown area, a dense core, I have lots of Wi-Fi hotspots through my mobile provider, and I can transmit that data quickly, efficiently, and cheaply. But when I'm out in a region that doesn't have that, I might have to use the LTE radio, which is more expensive both in power and monetary cost. And I want to try to minimize that for non-core data, non-critical data that I need to transmit. So I can have a flow running on the MiNiFi side that makes those decisions very quickly, makes it without any kind of external input, and then can transmit critical data over the LTE radio, but store the non-critical data, and when I get back within range of Wi-Fi, batch transmit that over Wi-Fi, right? So I'm saving money, I'm saving time, and I'm saving power on the device consumption. Now, all of a sudden, the brake temperature spikes, the velocity drops significantly, and some of the impact sensors go off. Well, I can have a flow that's set up to say, when I get these thresholds, I need to stop executing the other flows. I don't care about the radio station selection at this point. I want to start recording everything to a local buffer, because if I've lost network connectivity, I don't want to drop that data. I want it to maybe be recoverable from the vehicle itself. There's all kinds of inflection points that you can recognize using the flows written here without any kind of external stimulus or input from a network connected system. As the title of the talk is, Secure Command and Control, I do want to point out one of my favorite quotes from Oleg Shelejev, that the S in IoT stands for security. It's often not a consideration, both from device manufacturers, from platform integrators, or from developers at large. And I think it's something that really does need to be recognized and driven home, that we're collecting orders of magnitude more data now than we ever were before. And we're collecting that from endpoints that can be extremely sensitive and at times invasive. And proper security, not only around did we deploy TLS, did we deploy authentication and authorization, but threat modeling and risk analysis and going, what could be done with this data, right? We're very good at thinking about the positive use case. I want to do this, I will achieve this. But making sure that we understand what are the risks to ourselves as collectors and maintainers of that data, to users, whether that's an organization, a government, or individual people, and then groups of people at large, is a really important thing that I just want to stress here. So the functionality of actually exfilling that data, we have a number of ways we can do that. There's a protocol called site-to-site, which is proprietary, but it's an open source protocol. And that's how NiFi clusters communicate with each other, but that's also how MiNiFi instances communicate with NiFi. Provides mutual authentication TLS. It allows for the propagation of back pressure, which is a feature where if something's producing data too quickly for a downstream system to process it, that system can inform the previous processor to slow down and yield its execution time. And that back pressure can actually propagate all the way through a flow up to an original ingest point of data acquisition. It comes with two implementations. One is HTTPS, one is raw socket. The raw socket was the original, but a lot of people didn't like opening additional firewall ports in their AWS instances, so there's an HTTPS implementation as well. And there's also a concept of a heartbeat, and I'll talk about that a little bit later on, but that's these agents reporting back not the actual data they're collecting, but information about their running, their flow definitions, their capabilities, things like that. Finally, if you don't want to use site-to-site, you can use any number of protocols under the sun, HTTPS, FTPS, you can use MQTT or AMQP. There's writing to files, writing to ports, all kinds of things available. So again, we'll quickly go through some examples. Again, using healthcare as our foundation here. So need for immediate alerting. This one I think is really critical. If I am running a hospital, I'm getting all these sensor data. It's really fantastic that a year from now I can go back and extract patterns from what was happening. And maybe I had 50 different patients over the course of 6 months who all presented with the same symptoms, and half were given this medication and half were given this medication. And I can make real analysis on the benefits and downsides of each of those. That is an incredible use case, and that's very valuable. But if I'm in the hospital and my blood pressure changes or my heart rate changes, I don't want to wait a year for valuable information to come out of that, right? The need for immediate alerting is really, really critical in a healthcare space. So things like taking time series data and looking at threshold changes and being able to execute new functionality based on that is incredibly useful and incredibly important. You can't retroactively save somebody's life. We often talk about legacy hardware and being able to expand our reach and our functionality onto things that weren't necessarily built to do it. Again, in a hospital environment, the workstations are often multiple generations old, especially for things that connect to medical hardware. Those are validated and certified for a specific operating system, specific hardware, and it is extremely unlikely that they will get updated in the future, even if new vulnerabilities are discovered, new operating system updates are pushed out. So we're often running a lot of this specialized software on very old hardware, and that makes it difficult to extend the newest, latest, and greatest monitoring system onto that piece of hardware. With things like MiNiFi, you can push very small, very lightweight pieces of software onto these older systems. And then again, security person, edge data protection, being able to secure the data and offload it with minimal overhead, being able to redact that sensitive data at the edge. Maybe we are collecting things that we don't actually want to transmit over the network, as well as encrypting data per patient, right? I have 1,000 different people coming through here. If somebody cracks that initial key or master key that I'm using, all of those people are exposed. But by using something like a derived key, I can make sure that each one is protected similarly but uniquely, and I raise the level of effort needed for an attacker to violate that system. So, we don't have time for all the demos. Quick show of hands, who wants the hospital simulator, who wants the credit card reader? Hospital simulator? Credit card reader? Oh, slightly more, okay. So, this is a hotel in Melbourne, Australia, where they had a lot of problems with the box of wires and stuff that I brought in. So, what are we going to show here today? Using a magnetic stripe reader, the user is going to swipe their credit card. This device is connected to a Raspberry Pi. That's going to collect the data, and it's going to make some determinations on the kind of data, and then send it back to my laptop, which was functioning as the data center. This is the component list. Not really important, just to show that for about $50 you could build this. It's not like you have to go get some kind of enterprise hardware. So I designed two flows. One that's going to run on the MiNiFi side, on the data center host, and one that runs on the MiNiFi instance on this Raspberry Pi. The MiNiFi flow will receive data over that site-to-site protocol that I mentioned. It will take the credit card data, which I'm going to encrypt and decrypt it. It'll route all the other swipes, so like gift cards and driver's license, to a magnetic stripe reader data parser, and then convert all of it to JSON, batch it, and write it out to a file. On the MiNiFi side, where I'm actually collecting the swipe data, I'm going to detect which swipes are from a credit card and encrypt those, and then send everything to MiNiFi via site-to-site. So just a little screenshot of what that flow looks like. Again, this is not super simple if this is the first time you're seeing it, but it's also not incredibly complex. From the name of the processor, from the description of the processor, and the connections between them, even somebody who hasn't written a line of code can get the basic understanding of what's happening here. On the MiNiFi side, this is a flow that is 6 components, really only needs to be 3. 3 of these are in here for basically integration testing. It's collecting data from a file, it's encrypting certain pieces of that data, and then it's sending everything over site to site. This is all the code of the entire project. I know it might be hard to read on the screen, but it's available if you download the slides. It's a simple Groovy script that I wrote that does a little bit of detection on credit card numbers based on BIN and parses out the data format from track 1 and track 2. Really boring stuff if you don't enjoy doing it, but it's there for you if you wanted to apply it. So here's a screenshot of the code actually running on a Raspberry Pi, getting data swiped in. Here's the output on my MacBook Pro showing the credit card swipes and Starbucks gift card swipes and things like that. And then here it is running on the hotel's TV because they didn't really lock down their network that well. So, Cloudera Edge Flow Manager. This is going to provide a better integration between the two. Currently, we've talked about MiNiFi and MiNiFi as these 2 separate things where I build a flow, I push it out, I deploy it, I get data back. But that process comes from 2 disparate pieces of software developed for slightly different targets. With the Edge Flow Manager, I have an integrated environment where I can author these flows that are going to run on these distributed systems. I'm not building a flow that could run here or could run somewhere else. I'm building a flow that's explicitly designed to run on limited hardware with particular capabilities and report data back, not only the actual data it's collecting, but also metadata around its processing, its performance, its capabilities, and targets. The heartbeat monitoring that I mentioned earlier allows for you to see not just one device running remotely and how that's doing, but hundreds or thousands of devices at the same time. And you can even build your machine learning models, train them in your data center with data you've collected from thousands of devices, and then take the model definition and push that out to the edge so that now you can run it in network unconnected scenarios or on specific data collection that you're going to receive that's targeted and enhance the model for a specific use case. So in summary, what does MiNiFi provide? We're talking about the difficulty on repeatably and intelligently routing and collecting data, introducing platforms that allow non-developers to achieve their goals in this use case, and then extending that reach and visibility not just in our data center, but out to the edge where we're actually generating and collecting the data. LoPresto, thank you very much, and I appreciate your time.